Hey, my name is Eric Brown, and I am solving the universe. Today, we're going to talk about wave-particle duality. This discussion is not going to be about how wave-particle duality is this weird and core fundamental conflict that the universe has in exhibiting itself in kind of paradoxical ways, which is the way that a lot of people approach this topic. What I'm going to talk about is how wave-particle duality is a misconception in physics that we should honestly leave behind for the betterment of our race. And so today we're going to destroy wave-particle duality. All right, so wave-particle duality discussions in popular science and in early physics learning can start to go something like this, where you have particles. Particles have properties such as they are massive, they're small, but they have definite volume. They have kinematic behavior, meaning that there's a position, a velocity, and an acceleration that defines the behavior of this particle. They're rigid, meaning that they move as one distinct thing. They occupy space, meaning you can't stick two of them on top of each other, or the idea that one of them might exist in more than one place at the same time is incorrect, right? This is our concept of what particles are. Then on the other side, you have waves. We know that the universe can behave like waves sometimes. And waves are massless. The size of a wave is irrelevant. The wave itself exists across the entire medium that's waving. The behavior of a wave is determined by boundary conditions and wave equations, not by kinematic equations of motion, right? Waves are fluid, meaning instead of moving as one single distinct thing, they move as a continuum. There's a continuum of motion across the wave. And waves are overlapping, meaning they can exist on top of each other. And with this construction here, what I have just shown you is that there is this deep and fundamental paradox in the universe, because sometimes the universe behaves like a particle, and sometimes the universe behaves like a wave, and those two things, as we can see here, are completely diametrically opposite from each other. So there's some core conflict that the universe has. And I would like to dispense with that idea. And honestly, when we first started talking about this conflict, this wave-particle duality in quantum mechanics, it was in the early 1900s. And in the early 1900s, when we first started talking about this, one of the reasons that I believe we began that discussion at that time is because this dichotomy between waves and particles already existed. In the early 1700s, or not the early 1700s, in the 1700s, Isaac Newton began conceiving of a particle definition for light, because he could see that light traveled in straight lines. The rays of light were straight, and that kind of reminded him of this kinematic behavior where things travel in straight lines. And so he started building this conception. And he watched how things refract, and he said, well, this could be described by a certain type of transfer of energy from the light to its medium, that if you described it as a particle, you would be able to describe this refraction. Well, only a short time later, a successful wave theory of light emerged. And the wave theory of light actually was more successful than the particle theory. And this dichotomy did not last long in the 1700s, but it's a part of our history. And it's a part of our history that maybe that type of conflict, we as a human species like to hold on to that kind of stuff. But it's that was probably the origin of this newer version of that dichotomy. So the fact that it existed in our history. So in the 1700s, most of this dichotomy that we have established here was actually successfully removed. Right? The resolution was that waves can travel in little bundles called wave packets. And those wave packets can act like particles. That if you zoom out enough from the wave packet, the behavior that we see could be idealized by what we think a particle is. And so you can do something like this. You can say, well, yes, waves, their size is irrelevant. The wave exists across the entire surface of the medium that's waving. But a wave packet can be bounded, and the disturbance can be isolated to a single point, or to approximate it as a single point. And yes, the behavior of waves can be determined by boundary conditions and wave equations, but If what you're talking about is a wave packet, you can approximate a position and a velocity and an acceleration, and you can describe its kinematic behavior. You can even start to build dynamics and the ideas of forces and all that stuff. So yes, they're fluid, meaning that there's a continuum of motion across the entire wave. But if you're talking about one single wave packet, you can say that if we're approximating it, it's moving as a single unit. And yes, waves are overlapping, but in your early physics education, when you're learning about quantum mechanics for the first time, you start to learn about a concept called exclusion. And the concept of exclusion is that there are certain kinds of waves that the probability of having them overlap goes all the way to 0. And this ends up not being a quantum property. Like this exclusion principle, you can actually derive exclusion for macroscopic waves like water waves. So it's just a certain kind of wave. That these different kinds of waves cannot exist on top of each other. So the idea that they occupy space in what we might commonly think is the way that we occupy space, that's actually a thing. So we still kind of have this problem where we think of particles as being massless and we think of waves, or we think of particles as being massive and we think of waves as being massless. And that problem was kind of aggravated so the problem with this dichotomy was aggravated in around 1905 because we started talking about photons. And photons, like if you ever look up any early learning physics book or try to find if you were to say, let's conceptualize what a photon is, photons are usually depicted as little beans that have waves inside of them, right? Like some little ellipse. This is the usual depiction. There's a little ellipse. There's some little wave inside of it, right? And people think of photons as somehow being small but have definite volume and having kinematic behavior and being rigid somewhat and occupying space somewhat or whatever, right? That when we think about photons, that's what we're thinking about, but that's not it, guys. Photon behavior, the fundamental idea of photon behavior is that the energy is transferring in discrete packets, and that's it. That's the only thing that photon behavior is. It's not that light travels in little regions of space, that it's confined in space. That's not it at all. In fact, you could have a photon, so say I had a wave that filled all of space. That could be a photon. And what that photon is represented by is not by where it's at in space, it's represented by the amplitude of the wave. That for waves of a fixed frequency, the only thing you can change to change their energy is the amplitude. And so when we talk about photon behavior, we're not talking about little beans that have waves inside of them at all. That's never been it, ever. So what I'm going to say about photon behavior is that by plopping photons in the particle bucket, this was kind of a cheat. And I'll tell you why. That even if you believed that photons were little beans with waves inside of them, that the photon behavior is nothing like any particle behavior. The very specific thing we're talking about when we ever said photons to begin with was discrete transfers of energy. That is not how particles behave. That is not how they've ever behaved. Like up until this point, up until 1905, we would talk about collision between particles, and you could talk about elastic or inelastic collisions, and you could build scattering problems, and you could solve those problems. And energy with particles, according to our conception of particles in 1905, energy was transferred as a continuum, always. So, like the idea that energy is being transferred discretely doesn't actually map onto particles at all. The word discrete kind of does, right? So if you say, oh, photons are transferring energy discretely, you kind of start getting this picture in your mind, like if I got 5 discrete transfers of energy, it's kind of like that there were 5 particles there. And so there's this idea that maybe those particles, you could think of them as having, that they move or act as one thing, which is, that actually is true. But that one thingness, like because we know particles move rigidly as one thing and discretely, right? And that 2 particles kind of have these 2 distinct identities, I guess you could say. Maybe this was the reason that this photon behavior got thrown into this bucket. I actually think that just the word discrete was one aspect of why it got thrown in the particle bucket. The other reason was that we already had this history of a dichotomy between particles and waves. And due to that history, it kind of just got resurrected in this moment. And this is what I believe. But photon behavior does not really fit into the particle bucket, because in 1905, according to that conception of particles, no particle ever behaved like that, ever. Okay, so this other thing happened in 1905, which addresses this top issue here, where we started articulating the special theory of relativity. And we learned that there is a relationship between energy and mass. And as we learned more, what we learned is that this relationship is actually between the energy of a particle at rest. That you say, well, so you'd say there's the rest mass. What we started coming up with this term, we called it rest mass. And that if there was a particle that was not moving, that the energy of that particle could be entirely described by its mass. Well, we know that waves have energy, right? So waves actually do have energy. And you could say, well, but are waves ever at rest? That kind of does not jive with the idea of a wave. Actually, waves can be at rest. There is a concept of waves called a standing wave. And you can talk about standing waves, and you can talk about traveling waves. And a standing wave is a wave that it technically is not moving at all, right? Like if you imagine a guitar string, like if I pluck a guitar string, there's the fundamental mode of vibration where the string kind of bulges up like this and it comes down like this. And it's moving up and down like that, but along the string, it's not moving at all. So you could say in the dimension of the string that there is no motion, that the wave is not moving. And so this idea of being at rest is something that you could say waves do have this concept of being at rest. So I guess you could say you could do this. You could say, well, saying that particles are massive and waves are not massive really is a cheat. We can't do that. And saying that photon behavior explicitly resides within this particle bucket is also a cheat, because this doesn't actually describe any kind of particle behavior that we've ever observed ever. So to say that it's even necessary at this point to talk about particles, because there were no particle properties that were exclusively particle-esque that really describe the universe. That most of them, you could say, are just idealizations of certain kinds of wave behavior. And then the ones that we thought weren't wave behavior aren't exclusively particle behavior either. So the concept of particles, and I actually believe this, that the concept of particles is something that you could possibly dispense with. Or you could just treat it like it's a macroscopic only designation. Like when I'm talking about particles, I really am talking about pebbles. I'm not talking about subatomic relativistic entities, right? And so that we could start to exclude the use of particles, or at least the use of the behavior of particles, or the idea that there are such a thing as particle behaviors that are explicitly not wave behaviors, that we can start to do away with that idea. And what I currently believe is that this is how it works, is that waves can be described, or that mass can be described as a wave behavior, and that photons can be described as a wave behavior. And there's a lot of benefit in moving everything over to this side, and I will tell you why. That our definition of particles, up to the early 1900s, since the early 1900s, our definition of particles has changed quite a bit, and we'll talk about that a little bit later, but our definition of particles here came from the early Greek philosopher Democritus, who described this process of saying, if I take an object and I cut it in half, that the two halves of this object should have the same properties as the original object. And so I can keep kind of cutting in half and cutting in half and cutting in half, and extrapolating those properties down and down and down until I reach a point where I just can't cut in half anymore. And this was our fundamental, or our original idea of what an atom was, is something that you just can't cut in half anymore. It's atomic. It's indivisible. And that's this discreteness, right? Like this idea of discreteness. It's indivisible. It's atomic. Well, this is the problem. This basically means, like, this definition of particles is a complete extrapolation. So if we say, okay, we don't actually know what particles are, but we're going to extrapolate what we do know about how they must behave as we look at them in big, large clumps of them, but we don't really know what they are. So if we even decide to use particles as some type of fundamental picture of describing the universe, we're now handicapped. Because if I were to say, okay, let's say that there are particles, and let's say that they're massive. Okay, tell me why. Tell me why a particle is massive. You can't. Why not? Because you don't actually know what a particle is. Nobody knows what a particle is. It's an extrapolation from our macroscopic observations of the universe. That's it. Waves, on the other hand, are driven and defined by principles that we understand. They're very mathematically and rigorously defined. So if I say, well, okay, let's say that waves are massive, and now I want you to tell me, give me a wave description of what creates mass. Well, you can do it. And I have done that. And this was part of my senior thesis when I was in my undergraduate, was describing inertia and mass as a wave property. And I'll do another video on that. So what I've also discovered is that you can describe photon behavior as a wave property. And that deserves its own video as well, but I'll give you a little hint that when you think about, like, if you pluck a guitar string, that the waves that are allowed to exist on this guitar string are waves that satisfy the boundary conditions of the fact that this guitar string is fixed at both ends. And the waves that are allowed to exist are called modes. You can call them modes of propagation. And there are only certain allowed modes of propagation. So thinking of photon behavior, saying that there are discrete states of energy that can be transferred, that the wave has discrete energy states, is kind of the same thing as saying that it has certain allowed modes of propagation. And that the distinction between those two different ideas has to do with the fact that modes of propagation in our classical sense comes from boundary conditions in space. Whereas photon behavior, I believe, comes from boundary conditions in time. Now, that's not all there is to the story. We're actually going to get into that in a different video, but that's the teaser for what photon behavior is and why it's a wave behavior. Okay, so when I first started learning about physics, I started coming to this conclusion that the wave-particle duality was a mistake. Like, treating this like it's some kind of fundamental property of the universe actually puts us at a disadvantage. And the disadvantage comes from the fact that we have a colloquial definition of particle. And so every single time we have to think of something as being a particle, we have to fall back onto this colloquial definition that is not rigorous and therefore doesn't actually provide us with any good picture of what's actually going on. Whereas if we start to think of those properties as possibly coming from waves, well, we do know very explicitly how waves work. At the smallest scales, we know how waves work. So we're actually better positioned to describe things like mass or photon behavior rather than leaving them undescribed and just throwing them in the particle bucket. So I actually felt kind of alone, honestly. Like, I felt like that I was somehow some type of heretic and that I was violating or I was a rogue, and I was violating the physics orthodoxy. And I have since come to believe that that just is not true. And it's not true on two fronts. That there's a very large group of physicists who believe that it's just all waves and that that's okay. And not only is it all waves, but they understand that once you've kind of come to that conclusion, you're now in a better position to describe what the heck is going on. And for all those physicists who don't think it's all waves, who kind of think of things as being particles and waves, and they kind of still hold on to that idea, what those physicists have done is they've changed the definition of what a particle means. And they've changed that definition such that particles are essentially just waves now. Like the current definition of a particle is that it's essentially just a wave. And ultimately, it's a wave that exhibits this kind of behavior, right? That's all it is. And well, I mean, in a lot of physicists' minds, it's a wave that also exhibits this kind of behavior. So this is where I think that we are. It's all just waves. And for some physicists, they just are not yet describing these two properties as coming from waves, and so they're holding on to the idea of a particle. So I'm not actually alone in believing that we should do away with wave-particle duality. Here's a quote from a very prominent and respected physicist. This double nature of radiation is the wave properties, and of material corpuscles, which is the particle properties, has been interpreted by quantum mechanics in an ingenious and amazingly successful fashion. This interpretation appears to me as only a temporary way out, meaning that it's just a stepping stone. And that it's a stepping stone in our understanding. And as our understanding evolves, we could possibly safely do away with this idea entirely. And this physicist was Albert Einstein. So I'm in relatively good company. All right, so wave-particle duality destroyed. If you like this video, go ahead and like and subscribe. Share with your physics nerd friends. # solving the universe. Once again, I'm Eric Brown, and I'm solving the universe. See ya.